Why this solar breakthrough matters more than perovskites. Intellectual hook, the question we're not asking. For the past decade, one word has dominated conversations about the future of solar energy. Perovskite. It's been called the next big leap, the material that could finally push solar panels beyond silicon. Lighter, cheaper, more efficient, at least on paper. But here's the uncomfortable question we rarely pause to ask. What if the most important solar breakthrough isn't the one breaking efficiency records, but the one that actually survives the real world? Because energy transitions don't fail in laboratories. They fail outdoors, under heat, humidity, sunlight, supply chains, and economics. And that's where a far less famous material quietly enters the conversation. The root problem. Solar's growth is hitting invisible limits. Solar power is no longer experimental. It's mainstream. Roughly 7% of global electricity now comes from sunlight. Every year, hundreds of gigawatts of new capacity are added worldwide. From rooftops to massive utility-scale farms, solar has become one of the fastest-growing energy technologies in history. But this growth rests on materials that come with hidden trade-offs. Traditional silicon solar panels rely heavily on silver, those thin grid lines you see across each cell. Silver alone can add over 10% to the cost of a panel, and its price volatility creates long-term uncertainty. Thin-film alternatives like cadmium telluride avoid silver, but introduce new problems. Cadmium is toxic. Tellurium is scarce and expensive, closer in price to platinum than common metals. Perovskite solar cells were supposed to solve this. They use abundant materials. They absorb light efficiently. They've shattered lab efficiency records at breathtaking speed. But there's a catch. Perovskites struggle where solar panels must live, outdoors. Heat, moisture, oxygen, and ultraviolet light all degrade them. Even when encapsulated, long-term stability remains an open question. And many high-performing perovskites still rely on lead, complicating manufacturing, regulation, and recycling. So the real bottleneck for solar isn't just efficiency anymore. It's durability, scalability, and material reality. If solar is going to supply a much larger share of global energy, not 5%, but 30 or 40, the materials beneath it have to last, scale, and coexist with supply chains and environmental limits. That's where the story quietly shifts. A different kind of solar material. Imagine a solar material built not from rare or toxic elements, but from metals we already mine at massive scale: copper, zinc, tin, sulfur, or selenium. No rare earths, no exotic supply chains, no heavy reliance on toxic elements. This material already exists. It's called kesterite. Unlike silicon wafers, kesterite belongs to the family of thin-film solar materials. That means it can absorb sunlight using layers thousands of times thinner than traditional panels. To visualize this, think of sunlight like rain. Silicon panels need thick concrete slabs to absorb enough of it. Thin film materials are more like sponges, thin, lightweight, and efficient at catching photons. Kesterite's absorption coefficient is extremely high. Even very thin layers can capture large amounts of sunlight. That opens the door to lower material usage, lighter panels, and potentially cheaper manufacturing. But absorption alone doesn't make a great solar cell. The real question is whether it can convert that sunlight into electricity, and keep doing it year after year. Why kesterite is fundamentally different. What makes kesterite interesting isn't that it's new. It's that it solves problems that perovskites still struggle with. First, stability. Where perovskite materials tend to degrade under heat, moisture, and UV exposure, kesterite is remarkably resilient. In long-term outdoor field tests, including direct exposure to southern European sunlight, encapsulated kesterite cells showed minimal performance loss over several years. Even unencapsulated cells stabilized after an initial drop and then maintained performance under continuous illumination. That kind of behavior matters more than record-breaking efficiency numbers in a lab. Second, material safety. Kesterite does not require lead or cadmium by default. That simplifies manufacturing, reduces environmental risk, and makes end-of-life recycling far less problematic. And third, supply chain realism. All of kesterite's core elements are already mined and traded globally at scale. There's no looming bottleneck similar to silver or tellurium, no geopolitical choke points, no exotic extraction processes. In other words, kesterite looks less like a laboratory miracle and more like something that could realistically be manufactured by the millions of square meters. The efficiency question: where skepticism begins. Of course, none of this matters if the performance isn't there. For years, that's where kesterite fell short. While perovskite efficiencies raced past 25%, certified kesterite solar cells lagged far behind, hovering in the low teens. For a long time, that gap made kesterite easy to ignore. But recently, something changed. Not in a factory, not even in a prototype line, but in a model. Researchers used advanced simulations to ask a simple question. If every known limitation in kesterite were optimized, how efficient could it theoretically become? The answer was surprising. Under optimized conditions, with improved interfaces, reduced defects, and carefully tuned layers, kesterite solar cells were modeled to reach over 33% efficiency. That's not just competitive with perovskites. It's approaching the theoretical Shockley-Queisser limit for single-junction solar cells. And unlike many theoretical records, this result didn't rely on exotic or toxic materials. The model showed that near maximum efficiency could be achieved using mostly abundant, non-toxic elements. At that point, kesterite stopped being just stable but inefficient. It became something else entirely, a material whose biggest challenge might not be what it's made of, but how precisely we can make it. A different path forward. This is where the story becomes less about hype and more about patience. Perovskites exploded because they were easy to demonstrate in labs. Their crystal structures form readily. Early efficiency gains came quickly. Kesterite is the opposite. It's chemically complex. Its atoms are similar in size and charge, which makes perfect crystal formation difficult. Tiny defects can trap electrons before they reach the circuit. But complexity cuts both ways. The same material that's difficult to perfect may also be easier to stabilize, safer to deploy, and simpler to scale once manufacturing challenges are solved. So the real question becomes, is the future of solar defined by the fastest lab breakthrough, or by the material that can quietly endure the real world for decades? That question doesn't have an answer yet. But it's why kesterite deserves far more attention than it currently gets. And in the next part, we'll look at what's actually holding kesterite back, and why those obstacles may be more solvable than they first appear. The real barrier. Why kesterite is still stuck in the lab. The gap between theory and reality. On paper, kesterite looks almost too good to ignore. Abundant materials. No toxic lead, excellent stability, and now theoretical efficiency numbers that rival the absolute limits of solar physics. So the obvious question is, if kesterite is this promising, why isn't it already on rooftops? The short answer is simple. Because solar cells don't fail at the idea level, they fail at the atomic level. And for kesterite, the atomic details are everything. The hidden enemy. Recombination. To understand what's holding kesterite back, we need to zoom in, not to the scale of panels or factories, but to the scale of electrons. Every solar cell works the same way at its core. Sunlight hits the material. An electron gets excited and jumps free. That electron flows through a circuit, creating electricity. But there's a problem. Electrons don't like being free. If they find a shortcut back to where they started, they recombine with their positively charged counterparts, and the energy becomes heat instead of electricity. This process is called recombination, and it's the main efficiency killer in kesterite solar cells. In an ideal crystal, electrons and holes stay separated long enough to do useful work. In kesterite, that separation is much harder to maintain. Why kesterite is prone to defects. The challenge comes from kesterite's chemistry itself. Copper and zinc, two of its main ingredients, are frustratingly similar at the atomic level. They have nearly the same size and charge. As a result, during crystal formation, copper and zinc atoms often swap places. Imagine building a brick wall where half the bricks are subtly mislabeled. The wall still stands, but it's full of weak points. These misplaced atoms create what researchers call deep defect traps. They act like potholes in an otherwise smooth road, catching electrons before they can escape. And once electrons are trapped, recombination becomes far more likely. The problem doesn't stop there. Kesterite crystals can also contain vacancies, missing atoms in the lattice, which further disrupt electron flow. And at the boundaries between kesterite and the other layers in a solar cell, mismatched interfaces can introduce even more traps. All of this adds up to one result. Real-world kesterite cells perform far below their theoretical potential. The numbers tell the story. The gap is stark. While models suggest efficiencies above 30%, the highest certified kesterite solar cell efficiency so far is just over 14%. That's not competitive with silicon. It's not competitive with perovskites. And it's certainly not enough for commercial deployment. But this gap doesn't mean the theory is wrong. It means the material is unforgiving. In fact, many of the most important solar technologies went through similar phases. Silicon itself took decades to climb from single-digit efficiencies to today's mature designs. The question is whether kesterite's barriers are fundamental, or simply engineering challenges, repairing the crystal instead of replacing it. What makes recent kesterite research interesting is that scientists are no longer trying to reinvent the material. They're trying to heal it. One approach involves post-processing treatments, essentially repairing defects after the crystal has already formed. For example, thermal treatments in hydrogen-rich environments have been shown to dramatically reduce defect density. Hydrogen atoms can slip into the crystal lattice and neutralize problematic sites, preventing electrons from getting trapped. In another approach, researchers discovered that oxygen can fill sulfur vacancies in the lattice, smoothing out the electronic landscape and improving charge transport. Think of these elements as microscopic polishers, filling cracks and smoothing rough edges that electrons would otherwise fall into. The result? Higher voltages, longer electron lifetimes, and incremental but meaningful efficiency gains. The controversial shortcut. Alloying. There's also a more controversial strategy. Instead of insisting on absolute material purity, some researchers have experimented with tiny amounts of foreign elements. Small additions of silver, germanium, or even cadmium can help guide atoms into their correct positions during crystal growth. These elements act like scaffolding, temporary guides that encourage a more ordered structure, and the results are hard to ignore. Using these techniques, researchers have achieved record-breaking kesterite efficiencies in the lab. But there's a trade-off. Silver is expensive. Germanium is relatively rare. Cadmium is toxic. If the long-term goal is a solar technology based entirely on abundant, safe materials, these additives can't become permanent crutches. Still, these experiments prove something crucial. Kesterite can perform far better than we once thought, if its crystal structure is controlled carefully enough. Manufacturing, where costs are won or lost. Efficiency alone doesn't determine whether a solar technology succeeds. Manufacturing does. Historically, the highest quality kesterite films were made using vacuum-based techniques like sputtering. These methods are precise but slow, energy-intensive, and expensive. That's a problem. If a solar technology requires complex vacuum systems to function, it struggles to compete with silicon's massive optimized supply chain. But here's where kesterite surprises again. Recent record-setting kesterite cells were produced using solution-based manufacturing techniques, methods that are faster, cheaper, and far more scalable. One standout example is a process that's conceptually simple: applying excess material, then physically removing the surplus to achieve uniform thickness. It's low-tech in appearance, but incredibly effective. And it points to a future where kesterite could be manufactured using processes similar to coating, printing, or roll-to-roll production. That matters because energy transitions don't scale on efficiency alone. They scale on cost per square meter. What this phase really represents. Right now, kesterite sits at a critical stage. It's beyond pure curiosity-driven research, but it's not yet a commercial technology. In NASA's technology readiness terms, it hovers around the early middle levels, where materials are proven in principle, but not yet in products. This stage is often uncomfortable. Progress feels slow. Efficiency gains look incremental, and comparisons to flashier technologies like perovskites can make kesterite seem stagnant. But history suggests this is exactly the phase where foundational technologies are forged. Perovskites were in a similar position roughly 15 years ago, impressive in theory, fragile in practice, and uncertain in scale. Today, they're approaching commercialization. Kesterite may simply be earlier in its curve. The question: moving forward. So the real issue isn't whether kesterite can work. It's whether researchers can solve its defect problem without undermining the very advantages that make it attractive. Can we suppress recombination without toxic materials? Can we scale low-cost manufacturing without sacrificing quality? Can durability and efficiency advance together instead of trading places? Those are not easy questions, but they are engineering questions, not dead ends. And in the next part, we'll explore why kesterite's long-term impact might extend far beyond efficiency numbers, reshaping how we think about solar manufacturing, supply chains, and energy resilience itself. Why this breakthrough matters more than perovskites. When efficiency stops being the main story. For most of solar history, progress was easy to measure. Higher efficiency meant better technology. Lower cost per watt meant success. But as solar matures, that equation starts to break down. Once panels become cheap enough, efficient enough, and widespread enough, the limiting factors shift. The bottlenecks move upstream, into materials, manufacturing, logistics, and long-term reliability. This is the stage solar energy is entering right now. And this is where kesterite begins to matter more than perovskites. Not because it breaks records faster, but because it fits the next phase of scale. The supply chain reality check. Perovskites look ideal on paper, but scaling energy technologies is never just about chemistry. It's about what happens when millions of tons of material are needed every year. Many high-efficiency perovskite formulations still rely on lead. Even if the lead content per panel is small, scaling to global deployment raises serious regulatory, environmental, and public acceptance challenges. Encapsulation can reduce risk, but it doesn't eliminate it, especially over decades of weathering, mechanical stress, and end-of-life disposal. Kesterite avoids this entire category of problems. Copper, zinc, tin, sulfur, and selenium are already deeply embedded in global supply chains. They're mined on every continent. Their prices fluctuate, but they don't spike catastrophically under demand. That matters because energy transitions fail when materials become choke points. Silver is already a concern for silicon solar. Tellurium constrains cadmium telluride. Lithium and cobalt dominate battery discussions. Kesterite doesn't remove all material risks, but it spreads them across elements that the world already knows how to handle. That's not exciting, but it's how infrastructure survives. Manufacturing at scale isn't a lab problem. Another quiet advantage of kesterite is how it can be made. Perovskites shine in lab settings because they're forgiving. Their crystal structures form easily. Small-scale spin coating or vapor deposition produces impressive results quickly. But manufacturing millions of square meters of solar panels is not a lab exercise. It's a factory problem. Vacuum systems, tight environmental controls, and multi-step deposition processes all increase capital costs and reduce throughput. That's manageable for niche products, not for global infrastructure. Recent advances in kesterite manufacturing point in a different direction. Solution-based methods, coating techniques, and low-temperature processing open the door to roll-to-roll production. The same logic used to manufacture packaging films, flexible electronics, and large-area coatings. This isn't just cheaper, it's faster. Speed matters because the energy transition isn't waiting for perfect materials. It's constrained by how quickly we can deploy capacity at scale. If a material can be manufactured quickly, with less energy input, using simpler equipment, that advantage compounds over time. Durability is an economic feature, not a bonus. One of the least discussed aspects of solar technology is replacement. Panels don't just produce electricity, they lock in capital. When they degrade prematurely, the economics unravel. Perovskites have made real progress on stability, but long-term outdoor performance remains a concern. Moisture ingress, thermal cycling, and UV exposure are relentless. Kesterite's durability changes the equation. Field tests showing minimal degradation over years are not just technical achievements. They're financial signals. A solar panel that lasts longer doesn't just generate more energy. It reduces maintenance costs, simplifies warranties, lowers life cycle emissions, improves investor confidence. These factors rarely make headlines, but they determine which technologies utilities are willing to bet on. And utilities are conservative for a reason. The hidden advantage: design flexibility. Thin film materials like kesterite unlock design possibilities that rigid silicon panels can't easily match. Lightweight modules, flexible substrates, integration into building materials. These aren't just aesthetic features. They expand where solar can be deployed, on structures that can't support heavy panels, on curved surfaces, or in regions where transportation weight matters. Perovskites also promise this flexibility, but their environmental sensitivity complicates deployment. Kesterite's stability makes these designs more plausible in real-world conditions, not just controlled demonstrations. Again, this isn't about what looks impressive in a press release. It's about what survives outside. Technology readiness, a familiar pattern. There's a temptation to dismiss kesterite as too early. Its efficiency lags behind commercial standards. Its research base is smaller. Its name barely registers outside academic circles. But this trajectory is familiar. Silicon solar cells took decades to mature. So did lithium-ion batteries. So did wind turbines. Breakthrough technologies rarely arrive fully formed. They evolve through long, unglamorous phases where progress looks incremental and interest wanes, right before compounding effects kick in. Perovskites are further along this curve. Kesterite is earlier. That doesn't make it less important. It makes it strategic. Why this matters at a system level. Energy systems don't optimize for one metric. They optimize for resilience. A resilient solar technology is one that uses abundant materials, avoids toxic dependencies, can be manufactured quickly, survives harsh environments, scales without bottlenecks. Kesterite checks more of these boxes than its efficiency numbers alone suggest. This doesn't mean it will replace perovskites. It means the future of solar is unlikely to belong to a single material. Just as silicon, thin films, and emerging technologies coexist today, the next generation will likely combine multiple approaches, each optimized for different roles. Kesterite's role may not be record-breaking rooftops. It may be reliable, scalable, low-risk solar at massive scale. The real question isn't which is better. It's tempting to frame this as a competition: perovskite versus kesterite, speed versus stability, efficiency versus durability. But that framing misses the point. The real question is, what kind of solar technology does a decarbonized world actually need? One that looks impressive, or one that quietly works everywhere for decades? Perovskites may still dominate headlines. They may reach commercialization first. They may push hybrid designs forward. But kesterite represents something deeper, a reminder that breakthroughs aren't always loud. Sometimes the most important technologies are the ones that fit the system, not the spotlight. And in the final part, we'll look forward, not to predictions, but to what needs to happen next for kesterite to move from promise to impact. What comes next, and why the answer isn't obvious. The temptation to ask for a timeline. At this point, the most natural question is also the most misleading one. When will kesterite leave the lab and reach the market? It's an understandable impulse. We've been trained to think in release dates, roadmaps, and countdowns. But energy technologies rarely move on schedules that look clean from the outside. The more honest question is not when, but what has to happen first. And for kesterite, that answer has very little to do with a single breakthrough. Technology. Readiness is a series of gates. In energy research, progress isn't linear. It moves through gates. First, the material must prove it can work at all. Then it must work repeatedly. Then it must work outside the lab. Then it must work cheaply. And finally, it must work at scale. Kesterite has already cleared the earliest gates. Its physics is sound. Its stability has been demonstrated. Its theoretical efficiency ceiling is no longer in doubt. But it's still approaching the most difficult gates, the ones that decide whether a technology becomes infrastructure or remains research. Defect control, manufacturing consistency, long-term field data. These aren't glamorous problems, but they're the ones that determine real-world adoption. The quiet shift in research. Focus. One encouraging sign is how the research conversation around kesterite has changed. Early work focused on discovering the material. Recent work focused on understanding its limitations. Now the focus is shifting toward engineering discipline. How do defects form predictably? Which interfaces matter most? Which manufacturing steps introduce the largest losses? This is the phase where progress feels slow, but becomes cumulative. Every incremental improvement stacks on top of the last. That's how mature technologies are built. Lessons from perovskites. Without imitation. Perovskites offer a useful comparison, but not a template. They advanced quickly because they were easy to prototype. They struggled because they were fragile. Kesterite is almost the mirror image. Harder to perfect, easier to live with. The mistake would be to judge kesterite by perovskite timelines, or to force it into the same development path. If kesterite succeeds, it will be because it follows its own logic: stability first, manufacturability second, efficiency climbing steadily rather than explosively. That path isn't dramatic, but it's realistic. Where kesterite fits, if it fits at all. It's important to be honest here. Kesterite is not guaranteed to win. There are scenarios where defect suppression proves too difficult without sacrificing its material advantages. There are scenarios where perovskite-silicon tandems mature faster and dominate cost curves. There are scenarios where other thin-film technologies leap ahead. But there are also scenarios where kesterite quietly becomes indispensable. not as the most efficient panel on the market, but as the most deployable one. In regions where durability matters more than peak efficiency. In applications where material safety matters more than marginal gains. In manufacturing environments where simplicity beats precision. Infrastructure is rarely built from the flashiest option. It's built from the one that works reliably, at scale, under constraints. The bigger picture. Energy isn't a materials contest. It's easy to get lost comparing materials. Efficiency charts, cost projections, theoretical limits. But energy transitions aren't won by materials alone. They're won by systems that integrate technology, supply chains, labor, policy, and economics into something that can be deployed faster than the problem grows. Climate change doesn't care which material wins. It cares how quickly clean energy spreads. From that perspective, kesterite's importance isn't about outperforming perovskites. It's about diversifying our options. Resilient systems don't rely on a single solution. They layer multiple technologies, each optimized for different constraints. Kesterite could become one of those layers. The question we should be asking. So instead of asking whether kesterite will replace perovskites, a better question is, what kind of solar future are we actually building? One optimized for laboratory performance, or one optimized for decades of real-world operation? One dependent on delicate materials, or one grounded in abundance and durability? Those questions don't have clean answers, but they shape where investment, research, and policy attention flows. Why this story matters. Now, the most important thing about kesterite may not be whether it succeeds, it's what it represents. A reminder that technological progress isn't always about chasing the next record. Sometimes it's about stepping back and asking what really scales. As solar energy becomes a backbone of global infrastructure, the criteria for success are changing. Stability matters, materials matter, manufacturing logic matters, and breakthroughs that align with those realities may end up being more influential than the ones that dominate headlines. An open ending, on purpose. So will kesterite define the next era of solar energy? Maybe, maybe not. What's clear is that it challenges a narrow definition of progress, one that equates innovation with speed alone. The future of energy is likely to be built from technologies that are boring in the best possible way. Reliable, scalable, forgiving. Kesterite might be one of them. Or it might simply push the industry to think differently about what better really means. And that, by itself, would make it worth paying attention to.